friction and the coefficient of friction. Consider an object placed on a rough surface. We push on the object with a force P. Friction opposes the motion or the intended direction of motion. So because we're pushing left to right, friction will try to oppose this motion like this. As we increase the size of our pushing force P by pushing harder, the size of the frictional force will increase to try and oppose any potential motion. But friction can only increase up to a maximum value, whereas we can keep increasing the size of P by pushing harder. As we keep increasing the size of P, we reach a point where the object is about to move. It's on the cusp of moving. This point is called limiting equilibrium. So the resultant force is still zero, but the particle is about to break out of equilibrium. At this point, friction takes its maximum value, which can be calculated using this formula, F equals mu r, where r is our normal reaction force and mu is the coefficient of friction. The size of the coefficient of friction mu depends on the surface. A rougher surface will have a higher coefficient of friction. A less rough surface will have a lower coefficient of friction. If we make the modelling assumption that a surface is described as being smooth, i.e. frictionless, where friction has a negligible value so small that we essentially assume it's zero, then the value of mu is equal to zero. For example, we often state that ice has a mu value of 0. The coefficient of friction does not have any units. We can see that from the formula F equals mu r. F, of course, is measured in newtons. R is also measured in newtons. They're both forces. So to balance the units, mu has got to have no units. Let's do some examples. We're going to sketch a force diagram for each of these examples. So a particle of weight 30 newtons rests on a horizontal plane. I'm going to put in a normal reaction force vertically upwards like that. The coefficient of friction between the particle and the plane is 0.3, so mu equals 0.3. A horizontal force of P newtons is applied to the particle. Find P given that the particle is about to start sliding. So this terminology here is really important. It's about to start sliding. This is the key terminology that tells you that the particle is in a state of limiting equilibrium. This means that the resultant force is still zero, forces are balanced, but we're in limiting equilibrium, so the friction is equal to mu r. And the friction in my diagram will look like this. Let's now look at the forces vertically, look at the forces horizontally, and balance them. Looking at the forces vertically, the reaction force is equal to 30 newtons. Horizontally, remember we're in equilibrium, forces are balanced, P is equal to F. But of course, F is equal to mu r, which is 0.3 multiplied by 30, which gives us a value of 9 newtons. Example 2. A particle of weight 30 newtons rests in equilibrium on a rough horizontal plane. Let's start sketching this. So here is my rough horizontal plane. Here's my particle. Its weight is 30 newtons. I'll draw in the normal reaction force like that. A string is attached to the particle and makes an angle of 30 degrees with the horizontal. So that means there's a tension force like this. It could be in the other direction as well. I've just drawn the diagram this way. And there's an angle of 30 degrees. and the tension in the string is actually 18 newtons, so I can label that there. Find the magnitude of the frictional force acting on the particle and the coefficient of friction. So two things that we need to do here. Now, the tension force is pulling the particle in one particular direction. The friction will oppose the direction of motion or the intended direction of motion, so friction will look like this. We're going to need to resolve forces. So my T-force has a component that's horizontal like that and a component that's vertical like that. The component that's vertical we can see is opposite the angle 30 degrees, so will be 18 sine 30. The component that's horizontal here is adjacent to the angle, so will be 18 cos 30. So we have our two components. Again, remember the particle's in equilibrium, which means resultant force is equal to 0. Forces are balanced. So let's look at the forces vertically. So upwards we have R plus 18 sine 30, both acting vertically upwards, and they must be balanced by 30 newtons. So from here, which is the weight, from here we can work out R, which is equal to 30, take away 18 sine 30, which gives us a normal reaction of 21 newtons. If we now look at the horizontal forces, we can see that the friction is balanced by the horizontal component of the tension, 18 cos 30. So that would give us a value of the friction. If we want to, we can bring in some surds, exact values of cos 30, which gives us 9√3 for the friction. Now, if we know the system is in limiting equilibrium, F equals mu R, 9√3 equals mu multiplied by 21, which gives us mu equals 9√3 over 21, which we can calculate as a decimal, or we can leave it in surd form, simplified, 3√3 over 7. Example 3. A particle of mass 4 kilograms rests in limiting equilibrium on a rough plane inclined at 30 degrees to the horizontal. Find the coefficient of friction between the particle and the plane. Let's draw a force diagram. Here's my rough plane, inclined at an angle of 30 degrees. Here's my particle of 4 kilograms. I'm going to work out its weight, which will be its mass, 4, multiplied by the acceleration due to gravity, g. Remember, weight equals mass multiplied by acceleration due to gravity. We have a normal reaction force like that, which is perpendicular to the slope. And I'm going to add the components of the weight. So there'll be a component like that, which is perpendicular to the plane, and a component like that, which is parallel to the plane. And we can also fill in the angle. Now, if you're not sure about doing this, one quite nice way of thinking about it is to look at this right angle triangle. That's 30. This is 90, therefore this one must be 60, and because this is a right angle as well, this will also be 30. And that's the same for any situation like this. So let's think about the friction and the components of the weight as well. The weight of the particle is going to try and force it to slide or roll down the slope, which means friction must be acting in a direction that will oppose this motion, so friction must be acting in this direction. Let's put in some components. The component here is opposite the angle 30 degrees, so it's 4g sine 30. The component here is adjacent to the angle of 30 degrees, so it's 4g cos 30. We're then going to balance the forces. Remember, it's in equilibrium, so resultant force is equal to 0. We're going to balance the forces perpendicular to the slope. So R is equal to 4g cos 30. And then parallel to the slope, we can see that F is balanced by 4g sine 30. Remember, F equals mu R. So 4g sine 30 equals mu multiplied by 4g cos 30. We get some neat cancellation there. And then mu is equal to sine 30 over cos 30, which of course equals tan 30, or 1 over root 3. Example 4. A particle of mass 3 kilograms rests on a rough plane inclined at 30 degrees to the horizontal. So here's our horizontal, here's our particle, which has a weight of 3g, and the angle of inclination of the slope is 30 degrees. And immediately we'll put in a normal reaction as well. And we're in limiting equilibrium, which of course tells us that we'll be using both resultant force equals 0 and friction equals mu times normal reaction force. We are in fact also told that the coefficient of friction is 1/3, so mu equals 1/3. A horizontal force of magnitude x newtons is applied to the particle, so it is on the point of moving up the plane. Now, if this force x newtons is on the verge of pushing the particle up the plane, it must look like that horizontally. If that force x is attempting to move the particle up the plane, friction has got to oppose that. And remember, friction is always parallel to the surface of contact, so friction will work like that. Now, we need to put in some components. The components of the weight, again, are like this, perpendicular and parallel to the slope, and this angle will be 30 degrees. The force x, the horizontal force x, has two components as well. I'm going to draw them in. It's got a component like that, which is perpendicular to the plane, and it's got a component like that, which is parallel to the plane. I've drawn this diagram a little bit small, so I'm going to re-sketch it here. There is my force x, which is horizontal, and here's our slope. Here's the component that's perpendicular to the slope, and here's the component that's parallel to the slope. And the slope, of course, has an angle of 30 degrees. Okay, and there is our particle again. So let's work out these components. Now, looking at the angles, we can see that this force x is parallel to the horizontal, which means we have a pair of alternate angles. So this angle here is also 30 degrees. If you want to see it on the original diagram, it's this angle here. This will then allow us to work out our components. The component of x, which is parallel to the slope, is adjacent to the 30 degrees, so that component is equal to x cos 30. The component of x that is perpendicular to the slope is opposite the 30-degree angle, so that is x sine 30. The weight components we can do as we've done before, 3g sine 30 and 3g cos 30. Remember, we're in equilibrium. Let us balance the components of the forces. So parallel to the slope, we have F, which is acting downwards. We have 3g sine 30 also acting downwards, and they are balanced by this component here of x, which is x cos 30. Perpendicular to the slope, we've got r acting upwards or away from the slope, and that is balanced by x sine 30 and 3g cos 30. Now, there are lots of ways in which we can proceed. I'm going to rearrange this equation here to tell me that f is equal to x cos 30, take away 3g sine 30. Remember, we have the formula f equals mu r that we can use. So that tells me that x cos 30 minus 3g sine 30, which is f, is equal to mu, which we know is a third, multiplied by r, which is x sine 30 plus 3g cos 30. And what we're now going to do is rearrange this completely algebra so that we isolate x and then can work it out. So I'm going to multiply both sides by 3. So I have 3x cos 30, take away 9g sine 30 is equal to x sine 30 plus 3g cos 30. Collect the x terms on one side, 3x cos 30 minus x sine 30 is equal to 9g sine 30 plus 3g cos 30. Factorise the x out, so 3 cos 30 minus sine 30 equals 9g sine 30 plus 3g cos 30. Then use your calculator to work out the value of x, the division, and x comes to a value of 33.1547, etc., which is 33.2 newtons to 3 SF. A particle of mass 5 kilograms is released from rest on a rough ramp inclined at an angle theta above the horizontal, where sine theta equals 3/5. There's already a lot of information at this point, so we're going to start sketching our diagram. We'll make it a bit bigger than in the last example. So here's our slope, angle theta. So we know it's a particle of mass 5 kilograms. So here's my particle, and here is my weight of the particle, 5g. Normal reaction force perpendicular to the slope, which is r. And then the last piece of information we had was sine theta equals 3/5. Now, if I sketch a right angle triangle, there's theta. Sine theta equals 3/5, which means that the ratio of the opposite to the hypotenuse is like that, And of course we have a 3, 4, 5 Pythagorean triple, so this side must be equal to 4, and this means it's very easy to write down the value of cos theta, which is 4/5. You can of course also use your calculator to work out what theta is and go from there, but it's quite nice to have the exact values. Now, this time the particle's moving. It slides down the ramp and after 3 seconds has reached a speed of 4.9 meters per second. So what essentially has happened here is that equilibrium has been broken. We're no longer in equilibrium, so we cannot apply the resultant force equals 0. We're going to have to use Newton's second law of motion. If limiting equilibrium has been broken, that means friction will have reached its maximum value of mu r. Now, as the particle is sliding down the ramp, that means that friction must be opposing its motion like that. Let's put in the components. Let's put in the components of the weight like that and that. So this component is of course opposite the angle, so 5g sine theta. This one's adjacent, 5g cos theta. And I'm going to draw in the fact that we must be accelerating down the slope, and the direction of the acceleration will be down the slope like this. So let's have a look at how we're going to work things out. We're given some information here which I think we should have a look at. After 3 seconds, it's reached a speed of 4.9 meters per second. Now, the forces acting are constant. Constant force results in constant acceleration, according to Newton's second law of motion, F equals ma. And if we know we're dealing with constant acceleration, we can use one of the constant acceleration equations. Sometimes people call them the Suvat equations. So I'm going to write down everything that I know. I don't know how far it's travelled. I know it starts at rest, so initial velocity is 0. Final velocity is 4.9. Acceleration is what we're trying to find out, and the time is 3 seconds. So excluding s, because we don't have any information about it, we can use the Suvat equation v equals u plus at. So 4.9 equals a multiplied by 3, which gives us an acceleration value that is equal to 1.63 recurring. So we have our acceleration ready to use. Now let's take a look at the forces. If I look perpendicular to the slope, the forces have got to be balanced because there is no movement in that direction. So the reaction force R has got to equal 5g cos theta. And we know that cos theta is equal to 4/5. So that's 5g multiplied by 4/5, which is equal to 4g newtons. Now, parallel to the slope or along the slope, we do not say that F equals 5g sine theta. It doesn't. The forces cannot be balanced parallel to the slope because the object is accelerating down the slope. So we're going to use F equals ma, resultant force is mass multiplied by acceleration, and I'm going to choose a positive direction, which is down the slope, the direction of the motion. Now, in that positive direction, we have 5g sine theta. Now, friction is acting in the opposite direction, so it's negative, so we have 5g sine theta minus F, and that is our resultant force. 5g sine theta, which acts down the slope, and friction, which acts up the slope. This must be equal to the mass of 5 multiplied by the acceleration, which is equal to 1.63 recurring. And from here, we can rearrange this equation to calculate the friction. So my friction is equal to 21.23 newtons. I now have my reaction force over here. I have my friction over here. So I can now make use of F equals mu r, which of course applies because the limiting equilibrium must have been broken, and at that point friction has attained or achieved its maximum value of mu r once we're accelerating. So F is equal to 21.23 recurring, mu is what we're trying to calculate the value of, and r we know is equal to 4g. This gives us a mu value of 0.5416 recurring, 0.542 to 3 significant figures. Example 6. A particle of mass 2 kilograms rests in limiting equilibrium on a plane inclined at 25 degrees to the horizontal. Let's sketch this because there's quite a lot going on in this question and the situation will change in a minute. So initially, what we have is our plane. Here's our particle. Weight 2g, 2 kilograms, multiplied by the acceleration due to gravity. Let's instantly put in the normal reaction force, and we're inclined at an angle of 25 degrees to the horizontal. Now, it's in limiting equilibrium. The weight of the particle will essentially be trying to move the particle down the slope. That means that the frictional force must be acting to oppose this motion up the slope. Let's put in those two components, and again, as always, we know this angle is the same as the angle of the slope, 25 degrees. Let's fill in the components, so 2g sine 25, opposite the 25 degrees, 2g cos 25 degrees. So that's the initial state of affairs. The angle of inclination is decreased to 20 degrees and a force of 20 newtons is applied to the particle up a line of greatest slope. We need to make sure we understand everything that's happening here. So the situation is changing. Here's the slope again. Here's the particle. It's still got a weight of 2g. We still have a reaction force of r, but the angle is now 20 degrees. Obviously, these diagrams are not drawn to any kind of scale. Now, a force of 20 newtons is applied to the particle up the line of greatest slope. That means the 20 newtons is applied like that. And that is going to try and push the particle up the slope, which means the friction will now oppose that and be in this direction, down the slope. We'll put in the components of the weight again. This angle is the same as the angle of the slope, 20 degrees, 2g sine 20 down the slope, and 2g cos 20 perpendicular to the slope. So there's a number of things that we need to calculate. Find the particle's acceleration, first of all. So if we start with this, we need to have a look at the initial situation of limiting equilibrium, because this will give us some information we can then use. The slope doesn't change, it's just the angle of the slope that changes, and an additional force is included. So limiting equilibrium in the first scenario, perpendicular to the plane, we know that r is equal to 2g cos 25, balanced forces, equilibrium, remember. Parallel to the plane, we know that f is equal to 2g sine 25. Let's just correct that. And then we know that we can use F equals mu r to calculate the coefficient of friction. So 2g sine 25 is equal to mu multiplied by 2g cos 25, and this then gives us our mu value, which is equal to, a bit of cancellation here, sine 25 over cos 25, which works out to be tan 25. So that will be a useful piece of information to hold on to. So now, let's have a look at the second scenario where the particle is now accelerating. So we're assuming it's accelerating up like that. If we look at our forces perpendicular to the slope, we know that r is equal to 2g cos 20 now, because things have changed. They're still balanced because there is no motion in a direction perpendicular to the slope. There cannot be a resultant force perpendicular to the slope. However, if we look in a direction that's parallel to the slope, we have acceleration. So we're going to apply resultant force equals mass times acceleration, F equals ma, Newton's second law of motion. I'm going to choose up the slope as my positive direction. I have 20 newtons acting upwards, so that's positive. Take away F, which acts downwards. Take away 2g sine 20, which also acts downwards. This must be equal to the mass of the object multiplied by the acceleration, and actually we know what the mass of the object is. It's equal to 2 kilograms, so it equals 2a. Now from here we have to be able to work out F so that we can then work out the value of a. But of course F is equal to mu multiplied by r, and we know what mu is and we know what r is. So we can replace F with mu tan 25 multiplied by r, which is 2g cos 20. Take away 2g sine 20, which equals 2a. And from here we can calculate the value of a, which works out to be 2.3539 ... which we can round to 3 significant figures. Let's look at the last part of the question. When the particle has been moving for 2 seconds, the 20 Newton force is removed. Find the further distance the particle will move up the plane. So what we're going to do is work out a couple of things. Let's have a look at the situation before the 20 Newton force is removed. Now, we know we have constant forces acting, which means the resultant force is constant, which means the acceleration is constant. So because we've got constant acceleration, this implies we can make use of the constant acceleration or Suvat equations. So if we fill in the information that we have, we don't know how far it's travelled. We know it starts from limiting equilibrium before the slope is lowered and the 20 Newton force is applied, so its starting speed is 0, its starting velocity is 0. Its end velocity at the point at which the 20 Newton force is removed is v, we don't know what it is. The acceleration is 2.353 ... from previously, and the time is 2 seconds because it travels for 2 seconds before the 20 Newton force is removed. Let's cross out this, because actually what we're going to use is V equals U plus AT. And we're going to work out the velocity of the object at the point at which the 20 Newton force is removed. So it's 4.7079 ... meters per second. And now I'm going to draw another force diagram because, of course, the situation has changed. The 20 Newton force has been removed. The angle of the slope is still 20 degrees. Here's my particle. It has its weight downwards like that, 2g. Normal reaction force like so. This time, the 20 Newton force has been removed, but the particle is still going to travel up the slope for a little bit longer. It's got what we call momentum, which means it just has this residual velocity that allows it to travel up the slope for a little bit longer before it eventually comes to rest. So it should decelerate up the slope, come to rest, and then it will start to slide down the slope. So we're looking at the situation where after the 20 Newton force is removed, and because the particle is still travelling up the slope, friction is still going to oppose this motion and travel and be in the direction down the slope. Here are the components of the weight. Again, they haven't changed. So let's look perpendicular to the slope. Again, the forces are balanced perpendicular slope, so R equals 2g cos 20. So F is equal to mu R, which is equal to tan 25 multiplied by 2g cos 20. Now, parallel to the slope, we'll take up as being our positive direction, which means we have 2g sine 20, which is down the slope, so it's negative 2g sine 20, minus f, because they're both acting downwards, so in the negative direction, and that must equal the mass, which is 2 multiplied by the acceleration. Now, of course, we know what the value of the friction is, so we can substitute that in there. And from here, if we work out the acceleration, it comes to negative 7.64601, which makes sense because we were expecting the particle to decelerate up the slope. Now, again, the force is acting a constant. This is a constant acceleration, which means we can use SUVAT for the final part of the question. S is what we're actually looking for. U is the velocity with which it starts this period of motion, and that's the velocity we calculated earlier on. So it's 4.907 ... V, the final velocity, is equal to 0 because we want to know how far up the slope the particle travels before it's at rest. A is minus 7.646, and time we don't know, and actually we don't need to find it out. So from here, S, U, V and A, we can use the equation V squared equals U squared plus 2AS. And if we rearrange this equation to work out what S is equal to, it comes to a value of 1.4494, etc., 1.45 meters to 3 significant figures. So, example number 7. We have a block of mass of 1.6 kilograms placed on a rough plane inclined at an angle 45 degrees to the horizontal. Let's sketch a diagram to illustrate this information. Here is my block, mass 1.6 kilograms, so weight 1.6 g. Here's my normal reaction force R, and here's my angle 45 degrees. I will draw in the components of the weight. So this is 45 degrees. We have 1.6 g cos 45 and 1.6 g sine 45. We're then told that the coefficient of friction between the block and the plane is 1/4, mu equals 1/4. Find the acceleration of the block down the plane and the velocity after 2 seconds. So this gives us some additional information. We're told that the block accelerates down the plane, which means friction must be opposing this motion up the plane like so. So let's have a look at the forces perpendicular to the plane. We know that the forces are balanced. There's no motion, there's no movement perpendicular to the plane. There cannot be a resultant force, so the reaction force must be equal to 1.6 g cos 45. Parallel to the plane, we're going to apply the resultant force equals the mass multiplied by the acceleration, and we're going to take down as positive. This means that we have 1.6 g sine 45 down the plane, take away F, which is up the plane, and that must be equal to the mass of the object, which is 1.6 multiplied by the acceleration, which we are trying to find. We now have to work out what the friction is, which we can do using F is equal to mu multiplied by R. So the friction must equal 1/4 multiplied by the reaction force, which is over here, 1.6 g cos 45, which gives us a frictional value of 0.4 g cos 45, which we can substitute back in here. So 1.6 g sine 45 minus 0.4 g cos 45 equals 1.6 multiplied by the acceleration, which gives us an acceleration value of 5.1972, etc., 5.20 meters per second squared, to 3 significant figures. But we're not going to use the rounded value in the next part of the calculation. We have to find the velocity after 2 seconds, assuming the block starts at rest. Remember, the force is acting a constant. The resultant force down the slope is constant. Therefore, the acceleration is constant, which implies we can use our Suvat equations. Now, we don't know what the distance travelled is. We know it's starting from rest. The velocity is what we're trying to find. The acceleration is 5.19, etc. And the time is 2 seconds. So this tells me, if I exclude S, that we can use V equals U plus AT, substitute in the information that we have, and the velocity equals 10.394, etc., or 10.4 meters per second. Example 8. 2 particles, P and Q, of masses 0.8 kilograms and 0.6 kilograms respectively, are connected by a light, inextensible string. P rests on a rough horizontal table 0.7 meters from a smooth fixed pulley at the edge of the table. The coefficient of friction between P and the table is 0.25. The string passes over the pulley and Q hangs freely 0.5 meters above the floor. The system is released from rest. There is a lot going on in this question, and there are 4 things that we have to work out. So there is a lot of working involved here. We've got connected particles and a lot to think about. So let's sketch a diagram for the information that we have. So imagine this is my table and this is the ground level. So what we know is that P rests on the table. It's got a weight of 0.8 g and we have a normal reaction force upwards like that. And it's attached to a string which passes over a smooth pulley and connects us up with particle Q. Q has got a mass of 0.6 kilograms, so a weight of 0.6 g. Let's add in some forces. There has to be a tension in the string, pulling P in the direction of the pulley, which has got to be balanced by this tension here. Think about the modelling words. The string is light, which means it has negligible mass, and we can ignore the mass of the string, and it's inextensible, which means it doesn't stretch, which means the tension is constant throughout the string as we work out the problem. This also means that the acceleration of the objects when they move will be constant. P is 0.7 meters from a table. Sorry, 0.7 meters from the pulley. And the coefficient of friction between P and the table is 0.25. Because P is moving towards the right, the frictional force must oppose the direction of this movement and be in this direction here. Q hangs freely 0.5 meters above the floor, so Q is this distance above the floor. And this is the diagram that we're going to make use of. So there are lots of different ways of dealing with questions involving connected particles. This is the way that I am going to do it. I'm going to consider the forces acting on P first of all. Now, P only moves in a horizontal direction, but it is still worth us thinking about the vertical forces. So vertically, we know the reaction force must be balanced by the weight of P, so R is equal to 0.8 g. But horizontally, we know that P is accelerating in this direction once the system is released from rest, and of course Q is going to be accelerating in this direction. So let's take going to the right as the positive direction. We then have the tension in the positive direction, take away the friction, is equal to the mass of P, which is 0.8 multiplied by its acceleration. Now, can we do more than this? Well, we can. Limiting equilibrium must have been broken once the system was released from rest, which means that we can work out F using the fact that F is equal to mu R, and we know the fact that mu is 0.25. So F is 0.25 multiplied by R, which we know here. So F works out to be 0.2 g. And what I can do is then replace F in this equation here. So T minus 0.2 g equals 0.2 a. And I can't do anything further with that. We have two unknowns, T and A. So I'm now going to think about the forces acting on particle Q. And there's only one direction we can investigate here because Q moves downwards. We'll call that the positive direction, and we'll apply F equals ma. So we're applying Newton's second law of motion, again, like we did with P. Downwards, we have 0.6 g. Take away the tension, which is upwards, which equals the mass, 0.6, multiplied by the acceleration. And we don't know what that acceleration is yet. But we have a pair of simultaneous equations, call them equation 1 and 2, both containing the unknowns T and A. So we're going to add together equations 1 and 2, and see what happens. And we find that we get 0.4 g, the t's cancel out, equals 1.4 a. This then allows us to work out that the acceleration is neatly 2.8 meters per second squared, which answers our question to part A. We can then substitute that back into either equation, which gives us a value of the tension as 4.2 newtons. Make sure you show your working and calculate it carefully. We now have to calculate the speed with which Q hits the floor once the system is released from rest. So let's see what we can calculate. It's moving downwards, we'll call that the positive direction. Remember, the forces acting on Q, its weight and the tension are both constant, which means that the resultant force is constant, which means that the acceleration is constant. So we can apply our Suvat equations. So let's see what we have. We know Q travels a distance of 0.5 meters because it's 0.5 meters above the ground. U, the system starts at rest, so U is 0. V is what we're trying to find out, the speed with which Q hits the floor. The acceleration is the acceleration of the system, which is 2.8, and T we do not know, so we're going to ignore that. So S, U, V and A allows us to use the equation V squared equals U squared plus 2AS. Substituting in all these values gives us a velocity of 1.673 or 1.67 meters per second to 3 significant figures. And this is our answer to part C. Now, for part D, we need to calculate the distance P moves after Q hits the floor. Now, things change when Q hits the floor. When Q hits the floor, the string becomes slack, which tells us that there is no tension in the string anymore. T equals 0, it's no longer taut. If we look at P, it's still travelling along. But the force situation has changed. The weight is still 0.8 g, still has a normal reaction force like so, and it's still got momentum. As Q was dragging P towards the direction of the pulley, it's still got residual motion in that direction, which means that the friction still opposes this motion and is in this direction here. But we have no tension force anymore. So let's look at the forces acting vertically. R is still equal to 0.8 g. F is still equal to mu r, which means it's the same frictional force as before, 0.2 g newtons. But what has changed is we no longer have any tension in the horizontal direction. So if we take going to the right as positive, we're going to apply F equals ma. We have no forces going in the positive direction, but we have negative F here, which is the only force acting, which is acting towards the left, so it's negative. That equals the mass, which is 0.8 multiplied by the acceleration. But we can substitute in for F because we know it's equal to 0.2 g. And this then allows us to work out the new acceleration of the particle P once Q has hit the ground, and that is equal to negative 2.45 meters per second squared. We can then apply Suvat. Again, constant forces, constant acceleration means we can use Suvat. S is what we're looking for. U is going to be the same as the velocity with which Q hit the ground. Because the particles are connected by light inextensible string, during the part of the journey when they're both connected, they have the same acceleration, they have the same velocity. So the velocity with which P is left with at the point Q hits the ground is the same as the velocity with which Q hits the ground. So this is 1.673 etc. V we know is 0 because we want to know how far P travels before it is brought to a rest. Acceleration we've just worked out is minus 2.5, and T we do not know its value. So again, we're going to use V squared equals U squared plus 2AS. And from here we can then work out that S is equal to 0.5714 ... So 0.571 meters to 3 significant figures. A particle P of mass 5 kilograms rests on a rough inclined plane of an angle theta where sine theta equals 3/5. The coefficient of friction between P and the plane is 1.8. P is connected to another particle Q of mass 4 kilograms by a light inextensible string passing over a smooth fixed pulley at the top of the slope. Q hangs freely 2 meters above a horizontal plane. The system is released from rest with the string taut. Assuming that P does not reach the pulley, find these 3 things. This calls for a very clear diagram. So here is our plane, inclined at an angle theta. P sits on the plane, connected by the string to a pulley, which passes over the pulley and is attached to a particle Q like so. Now, forces acting. P has got a weight of 5g. Q has got a weight of 4g. They're connected via this light inextensible string, so there must be a tension like that and a tension like that. We have a reaction force like that for P, and then the system is released from rest. That means that Q will accelerate downwards like that, so P is going to accelerate up the slope like that. Remember, friction opposes the direction of motion, which means that friction has got to be in this direction here. What else do we know? We know that sine theta equals 3/5, so the opposite and the hypotenuse have to have the ratio 3/5. This is a Pythagorean triple, a 3, 4, 5 triangle, so the adjacent must be 4 and cos theta must equal 4/5. We're also told that the coefficient of friction mu is 1.8. We'll use that shortly. And the system is released from rest as the string is taut. Oh, one last piece of information. Q is 2 meters above the ground. And just to be clear, this is my pulley. So we're going to look at the particles separately. We'll start by looking at the forces on Q. It's a little bit easier to deal with as we only have one direction in which the forces are acting. Let's take positive as downwards. So forces on Q, we'll take down as the positive direction. We have 4g downwards, t upwards, so 4g minus t equals mass times acceleration. Remember, we are using F equals ma, Newton's second law of motion. So that's equal to the mass, which is 4, multiplied by the acceleration. We don't know the value of that. We have an equation in 2 unknowns. I'll call it equation 1. We do not know t, the tension, or a, the acceleration. Let's now look at the forces on P. Now, what we haven't done is to resolve the weight into 2 components. This angle here is theta. So we have 5g sine theta, opposite theta, and we have 5g cos theta, adjacent to theta. Let's look at the forces in a perpendicular direction to the slope. So perpendicular to the slope, there is no movement. forces are balanced, there's no acceleration, r must be equal to 5g cos theta. Now, in a direction parallel to the slope, we know that p is accelerating up the slope. We'll take up as a positive direction. And let's look at our forces. So we have tension acting up the slope, take away friction, which is down the slope, take away 5g sine theta down the slope, and that must be equal to the mass 5 multiplied by the acceleration a. And we have a second equation in two unknowns, t and a. Theta is not unknown. Now we need to find the value of f before we can proceed any further. Remember, the objects are accelerating, the system is in movement, so we can use F equals mu r. So our friction is equal to mu, which is 1/8 multiplied by the reaction force that we worked out, which is 5g cos theta. But of course, we know that cos theta is equal to 4/5, so that gives us a frictional value of 1/2 g. We can then substitute this back into equation 2, which gives us t minus 1/2 g minus 5g multiplied by 3/5, because we know that sine theta is equal to 3/5, is equal to 5a. And if we take this equation and this equation together, dealing with them simultaneously, if we add these two equations together, we will see that the plus and minus t cancel, and we are left with 4g minus 1/2 g minus 3g equals 9a. From here, you can work out that the acceleration is 0.54 recurring meters per second squared, and that's the answer to part A. Now, part B wants us to work out the time taken before Q hits the plane. So remember, the force is acting a constant, which means that the acceleration is constant, which means we can apply the constant acceleration equations. So looking at Q, particle Q, it's moving downwards, so down is the positive direction, S, U, V, A, and T. For our SUVAT information, Q travels 2 meters before it hits the ground. U is 0, the system was released from rest. V, we don't know what the speed of Q is when it hits the ground. The acceleration we've just calculated, it's 0.54 recurring meters per second squared, and the time is what we are actually looking for. So this is the one that we want. We can rule out V. So this gives us the link between S, U, A, and T, which means we're using S equals UT plus 1/2 AT squared. So 2 is equal to 1/2 a multiplied by t squared. Very, very simple equation. Rearrange this, and t equals 2.7105, etc. 2.71 seconds to 3 significant figures. Part C. We have to work out the total distance that P moves up the plane. So, if we think about the situation again, here's particle P attached via a string to particle Q. Particle Q travels 2 meters and then hits the ground, which means P must travel 2 meters and then a further distance once the string is slack because Q has hit the ground. Let's write that down. Now, let's look at the motion before Q hits the ground. So this really links back in with part B. Remember we were doing a constant acceleration calculation. Going back to that Suvat equation, taking down as positive, S was equal to 2 metres, U was equal to 0, V we don't know, but I'd like to work it out now. The acceleration A we had calculated and we were using it, and we know what the time is, but we're not going to use that calculation. We're going to look at S, U, V and A, and we're going to use the formula V squared equals U squared plus 2AS. We could use V equals U plus AT as well. It doesn't really matter, we'll get the same answer. And from here, we're going to work out what V is equal to. And if you substitute in the information, you will find that V equals 1.4757. Now, this is the speed with which Q hits the ground, but it's also the speed P is travelling at when Q hits the ground. Remember, they're connected by this light, inextensible string, so they have the same acceleration at the same time and the same velocity at the same time before Q hits the ground. Now, let's think about the motion that happens when Q hits the ground, or after Q hits the ground. The string now becomes slack. It's no longer taut. So this tells us that the tension is now equal to 0. Let's have a look at P. Still has its weight of 5g, still has a normal reaction force of R. There's no tension, but the particle is still accelerating up the slope. It's still got momentum, it's still moving up the slope. So friction must be acting down the slope. Let's put in the two components of the weight again. So we have them ready for use. So what we're going to do is look at the forces on particle P, and I'm going to have a look at the forces in the direction parallel to the slope. I'm going to take up as the positive direction, and I'm going to apply F equals ma. So we have minus F minus 5g sine theta, and that's equal to 5 multiplied by the acceleration. Now, if you recall, the reaction force has not changed. It's still equal to 5g cos theta. So it's still equal to 5g times 4/5 or 4g. F is still equal to mu r. So the friction is still equal to half g. It hasn't changed value. So minus a half g minus 5g multiplied by sine theta equals 5a, and from here we can work out the new acceleration of P once Q has hit the ground. This works out to be minus 6.86 meters per second squared. Of course, P is decelerating. So what do we do now? We wanted to work out the distance travelled. So again, we can apply a Suvat equation to do this, because the forces are constant, therefore the acceleration is constant. S, U, V, A and T. S is what we are looking for. U is the speed P is travelling with in the part of the journey before it comes to rest. So U is actually the speed that P is travelling with when Q hits the ground, which we worked out. It was 1.47, etc. V is 0 because we want to know how far P travels before it comes to rest. The acceleration we've just worked out is minus 6.86 meters per second, and the time we don't know, and we're not going to calculate it. So we can use V squared equals U squared plus 2AS again. This time we are calculating the value of S, which is 0.15873, and of course the total distance is this plus the 2 meters that P moved up the slope before Q hit the ground. So that gives us an answer of 2.16 meters to 3 significant figures. And this is our answer to part C. So let's draw a very clear diagram for this last example. We have a rough plane inclined at an angle of 30 degrees above the horizontal. We have a pulley fixed to the end there and a string that passes over the pulley like that. We have a particle A here resting on the plane, and B is hanging vertically from the other end of the string. There's got to be a normal reaction force here, and there's got to be a weight here. So A has a weight of 5g, B has a weight of 6g, and we know that there is a tension in the string like that, pulling B upwards, and a tension in the string like that, pulling A up towards the pulley. Now, we know that B hangs 1 meter above the ground, and the system is released from rest with the string taut, and B takes 2 seconds to get to the horizontal plane. The system is accelerating like this. B is accelerating downwards, A is accelerating up the slope, which means the friction must be acting to oppose the motion like that. And as a final step, let's draw in the 2 components of the weight. The angle here is the same as the angle of inclination. This is 5g sine 30. This is 5g cos 30. So we're going to look at forces on A. We're then going to look at forces on B, and we're going to use some Suvat equations and calculate the answers to part A and part B. So we need to find the coefficient of friction between A and the plane, so find mu, and the total distance that A moves up the plane. So A will accelerate for a certain distance, B will then reach the plane, the string will become slack, and A will continue to move. So let's start off by looking at the forces acting on B, which is a slightly easier thing to look at. Let's take down as positive. Acceleration is down in that direction. We're using Newton's second law of motion, F equals ma. So downwards we have 6g, tension we have upwards. That must equal the mass 6 multiplied by the acceleration a. I'll call this equation 1. 2 unknowns, t and a. We know where this is going in the direction of simultaneous equations. So forces on A, let's take a look at that. Now, perpendicular to the plane, we've got no motion. The forces are balanced. R must be equal to 5g cos 30. Parallel to the plane, we know the particle is accelerating up the plane. Let's take up as positive, that's the direction it's moving in. And we have tension upwards, minus friction downwards, minus the component of the weight parallel to the slope, and that must equal the mass multiplied by the acceleration. We'll call this equation 2. Now I'm going to add together equations 1 and 2 to see what happens. Now you'll notice when we do this, one equation contains positive t, one equation contains negative t, they will cancel out. And we will be left with 6g minus f minus 5g sine 30 equals 11a. Now, where do we go from here? We still have F as an unknown, we don't know the coefficient of friction, and we don't know the acceleration. But we are given some information about particle B. We are told that B takes 2 seconds to travel 1 metre to the ground. Now, the forces acting on B are constant, the tension and the weight, so the acceleration is constant, so we're going to use the SUVAT equations, the constant acceleration equations, to find out the acceleration. The distance travelled S is 1 metre, U is 0, the system starts from rest. We don't know what V is and we're not going to need it just for the moment. The acceleration is what we're actually trying to look for, and the time is 2 seconds. So if we look at that, we've got S, U, A and T, which gives us S equals UT plus a half AT squared. So that's 1 equals a half A multiplied by 4, which gives us an acceleration of 0.5 meters per second squared. Now, this is good because what we can do is substitute that into this equation here. So that gives us 6g minus f minus 5g sine 30 equals 5.5, and this gives us an f value of 28.8 newtons. Now remember, F equals mu r, so 28.8 is equal to mu multiplied by 5g cos 30, and this then allows us to work out mu, which is 0.6786, which is 0.679 to 3 SF. And we've completed part A. We've calculated the coefficient of friction between A and the plane. Now, part B, we need to calculate the total distance A moves up the plane, assuming A does not reach the pulley. So let's think about what happens before B hits the ground. A travels 1 metre up the slope. We can work out the velocity of B with which it hits the ground, which is the velocity of A at that moment. So if we use SUVAT again, we know that S is equal to 1, U was 0, V is now what we're trying to work out. The acceleration, we know it's equal to 0.5, and the time we also know is 2 seconds, so we can use any SUVAT equation that we want to use here. We're going to use V equals U plus AT because it's nice and simple to use, so V equals 1 metre per second. So that is velocity with which B hits the ground, which is the same as velocity of A at this moment. So what are we going to do? We're going to think about what happens when B hits the ground. So the string becomes slack, which tells us now the tension is equal to 0. We need to now look at the forces acting on particle A again, because the situation has changed a little bit. Some things are in fact just the same, so we have the reaction force up here, we have the weight of A, which is 5g, and of course the angle of the slope still remains at 30 degrees. Here are the components of the weight. And of course A is still accelerating up the slope, so let's put the friction in place down the slope like that. Now, R is still equal to 5g cos 30, that has not changed. F is still equal to mu r, So F still takes its value of 28.8 newtons that we worked out previously. But what has changed is we need to apply F equals ma again, taking up the slope as positive. We now have minus F minus 5g sine 30, both of these going down the slope, equals the mass of A, which is 5, multiplied by the acceleration, which will be different to the acceleration that we had previously, because the string is now slack, the situation has changed. So if we recalculate this acceleration, this comes to negative 10.66 meters per second squared. And we can then use this with another Suvat equation to work out the distance that A travels up the slope before it comes to rest. And again, we're assuming it does not reach the pulley. So let's identify what information we have and what we need to calculate. S is what we are actually looking for. U is the speed with which A starts the second phase of motion, which is the speed with which B hit the ground. It's the speed that A had at that moment, which we worked out was 1 meter per second. V is 0, it's coming to rest. A is negative 10.66, and T we don't know, and actually we don't need to work it out. V squared equals U squared plus 2AS again. Substituting in your information into this and rearranging, S equals 0.0469, which means that the total distance that A travels up the slope is equal to 1 plus this number, which is 1.05 meters to 3 significant figures.